All right, everybody. It's about 5:15, so we're going to get started for today. So welcome back to week 6 of the Deep Learning Decal. We have some very exciting things in store for you. So today we're going to be talking about autoencoders and representation learning. So a breakdown of the agenda today is pretty simple. Right, yeah. So the project proposal is due today, I believe, and on Gradescope, your group just needs to make one submission. So just one submission by one person in your group. Please make sure to include everybody in your group's names in your proposal submission. Yeah. Anyway, so today we're going to talk about autoencoders, some special types of autoencoders, and some topics in representation learning. So let's get started. So up until this point, most of the things we've seen in this class have a place for you to insert an input, and this is going to be some quantitative representation of your data. And then after that, you're going to apply some transformations and some nonlinearities to your data, and in the end you get an output. And the output is usually going to be used for these sorts of tasks: classification, regression, translation, segmentation. And most of these are all supervised learning. So you have to provide a label, which is more or less a correct answer, what you want your model to actually do. And your model will give an output that is probably not quite your label, and then you're going to train your model based on the difference between your label and your output. So this entire paradigm is called supervised learning. And you can do all sorts of great things with supervised learning, because if you want to identify, for example, what is that digit, then you apply all these complicated things, and in the end, you have a label that goes with it. And the label is not the same thing as the image. It's supposed to be something that the model is supposed to learn about the image and provide an answer. But today we're going to do something that's mostly in the realm of unsupervised learning. So in unsupervised learning, you don't actually have a label, but you're still trying to extract meaningful information about the data that you've been given. And so, for an example, this is a clustering task in like traditional non-deep learning machine learning, where there is no label, and it's up to you to decide how many clusters you believe the data is actually clustered in. And all of that work is done by the model without any sort of supervision. And so today we're going to be discussing a lot of deep learning models that have this principle kind of backing them. So an autoencoder is a neural network whose objective is to copy its inputs to its outputs. So in a sense, when when an autoencoder is given data, it's also given the label of the data because the label is the data itself. So, but there are lots of things that there are lots of ways that you can make this more interesting. So, generally, the way an autoencoder works is that you want to build two parts to this network, or implicitly, your autoencoder will have two parts to it. One part is responsible for doing some sort of encoding, and the second part is going to be doing some decoding. If you didn't have these two separate parts, then your autoencoder would just be basically a glorified identity function, where you're just multiplying your data by 1, so to speak. So in order to make the task of the autoencoder more interesting and even worthwhile, there needs to be some notion of encoding and decoding of your data. And the way you would train it is basically just comparing the difference between your output and your input. And since they ought to be the same, this loss function is very intuitive to understand. So if your functions f and g are parameterized jointly by a set of parameters theta, then the loss with respect to theta is simply the difference between the output, which is the composition of g f of x, minus the input x squared. So this is a very standard intuitive way to measure the loss of your autoencoder. Does anybody have any questions about anything I've covered so far? Yes?
Could you get an example for what you would encode and then decode?
Yeah, so for example, right here, maybe for some reason that I haven't really explained yet, and it's not entirely intuitive why you'd want to do this, but your input could just be this picture, the digit 3, and maybe you want to train the autoencoder to take in a digit and non-trivially encode it, and then non-trivially decode it and spit back the exact same image. And while it doesn't seem like that has any practical use, it is actually very useful. Much like how clustering is useful, right? Even though it's like, why are you doing clustering, right? Anyway. So this is not a totally new idea. We've actually talked about encoding and decoding in this class before. So in I think it was week 3 that we talked about RNNs. One important way that you can use RNNs is to treat recurrent networks as encoding and decoding functions. So examples would be if you're doing translation or paraphrasing or any other language-based task where you have embeddings of words and you feed them into one RNN network, which is acting as an encoder, and it's being encoded into some latent space from which the decoder will do predictions. So your embeddings could be in one language and your decodings could be in a separate language, right? So this is just to remind you that encoding, decoding is actually a pretty common theme in deep learning. But I guess here the specialty is that you're going to be encoding and decoding to get your input. So the most standard way to have an autoencoder is to have a network such that the hidden layer is going to be a lower dimensional space than your input layer. And so this is like probably the most intuitive constraint that you would want to apply to an autoencoder. Otherwise you could just do whatever you like. It would be far too easy for an autoencoder to reproduce its output if you didn't apply a constraint, something like this. So now the network must learn, given the training data, how can you effectively compress the training data into a constrained space, and then also how do you effectively decode something from your compressed space back to the original dimension. So from this framework, an autoencoder is forced to learn representations of the data. So if you've taken some linear algebra course, then you've probably heard of this idea of PCA, principal components analysis. So that the typical use case for that is you have a matrix in some high dimension, and in the hypothesis, and you can describe the matrix as basically multiples of, or it's spanned by a bunch of different vectors. And then some of those vectors actually do more to explain the variance inside of the matrix than others. So if you just take like the most salient ones of those vectors and you reparameterize the matrix as like a factorization of that, then you actually reduce the dimensionality of the matrix. But this is a linear operation. So basically the autoencoder can be learning a much more generalized version of PCA if done correctly. So visually, it's very easy to understand why it looks this way, right? So actually, most of the times when we do deep learning, we see that the hidden layer is actually larger than the input layer. Usually because what you want to do is you want to expand the input into a place where the model can play around with it more, where it has more options and more expressive capability. But here you want to do just the opposite. You want to force the autoencoder to actually think about it very carefully, like what is the actual essence of the data that it's being given, and how to effectively manipulate that from start to finish. Does anybody have any questions about undercomplete autoencoders? Yeah, this is pretty simple. So, but the problem is, because it's so simple, you actually run into a lot of issues. This all sounds very good in paper, and if deep learning models always did what we wanted to, then this would be it. We wouldn't need anything else, because it would just learn a generalized version of PCA and whatnot. But the problem is that if you remember the reconstruction loss, it just has two things in it. It has the g of f of x and x, right? So it has the output and the input. So it has this, and that's what it's comparing. But the reconstruction loss actually doesn't care about what happens in the middle. It's completely indifferent to the statistics and the characteristics of the actual encodings themselves. So as a result, the reconstruction loss doesn't encourage autoencoders to build good, meaningful representations. And so you might be thinking, well, that's okay though, right? Because we're still forcing the representation to be in a lower dimensional space. And that's always a good thing, right? Because if you can compress data, then you have to be learning something useful about it. So an example that was actually in the deep learning textbook is this. What if the hidden layer actually just has one unit in it, right? So it's one-dimensional representation. And somehow the autoencoder learns this mapping, that for data point number I, we're going to map it to I. And then from I, we will somehow reconstruct data point I, right? So the index is going to be its representation, but the index itself doesn't have anything meaningful to say about the data, right? Like there's nothing necessarily good about data, like there's nothing actually necessarily similar about data points 4 and 5 and 6, that they should be close to each other, right? And maybe data point 1 and data point 10 are very close to each other, but they're mapped to 1 and 10, right? So this is a pathological case, and it's not exactly realistic, but there's nothing about the reconstruction loss that would actually stop this from happening, right? So the vanilla reconstruction loss isn't very theoretically justifiable, because there are still lots of ways in which an autoencoder could devise loopholes in which it doesn't learn anything useful, but it still does well on reconstruction. Does anybody have any questions about this? So really what we're getting at is that we want our autoencoder and our models to learn something called a manifold. So a manifold is a topological space, you can think of it, and all along that space, there's very high probability of our data belonging to that area, right? So you could imagine like a paper, like a piece of paper that's in 3 dimensions, but all around the paper is where the data actually lies. And if you're off of the paper, then data really ought not to be there. And so we want to impose some constraints and some complexity on our autoencoder to actually try and learn something precise like a manifold. And so because like on a manifold, there are only some directions where data continues to exist, you want to learn those directions that explain the actual variations in the data. So a visualization of a manifold like this, where I was talking about the papers like this, what you have is really you have data that can be explained in only 2 dimensions, but it exists in 3 dimensions, right? So there's a pattern where if you're on this surface in 3 dimensions, then it's very likely that you belong to the training data set. And now you want a way to actually characterize that, oh, in fact, this data can be adequately represented with only 2 dimensions. And then you want to learn that mapping from 3-dimensional space to 2-dimensional space, right? And now if you look on this, this roll thing, at any given point on there, there are certain directions where if you go in those directions, you will remain on a data manifold. But if you go perpendicular to those directions, you're no longer on the manifold, right? You'd be like coming off of it. So now you want your network to learn the directions and the variations that actually give rise to the shape of this manifold. So this is very abstract. You're probably never going to actually visualize a real manifold. But this is what we want our networks to be doing. Because if you had that ridiculous index mapping function, then it wouldn't be learning anything close to this, right? Because if you moved in some direction in the latent space, it wouldn't tell you anything meaningful about where the data is. So generally, what we want to do is we want to apply regularization. So regularization aims to strike a balance between two things, right? Generally, you apply regularization on algorithms when you feel like they're overfitting. And that's basically what the autoencoders were afraid of them doing, is that they would be overfitting to our training set, because when we give them test data, then the representations that they've learned would be bogus. So now we're going to apply regularization to help them generalize better. So it helps to think of, so earlier we were talking about autoencoders as having an encoding and decoding function. But really we could just have them, we could think of them as encoding actually a probability distribution. That given some input x, the likelihood of the particular latent space variable given, so like the encoding function is basically giving you this probability function of given some input variable x, what would the latent space variable look like, right? And then it would basically give you a point estimate, the highest probability that this is what it probably looks like. So you can think of these autoencoders as being sort of random or stochastic. So the generative model is the model that is doing the decoding, right? So imagine if you had the latent space and you just simply sampled from it. Then you could theoretically just generate data out of like this sort of latent space area. And you want to maximize the probability that an output actually is, you want to maximize the relationship between the input, the latent space, and the output. And so the likelihood of any particular combination of output and latent space can be broken down like this using Bayes' rule. And if you want to find the most likely x, then you want to basically maximize this probability quantity. And so then if you look in here, right, maximizing this means maximizing these two quantities. And now we can actually look at this quantity right here, which is basically a prior over the latent space variables. Now, if you can kind of use that to your advantage, then you can have a regularizing effect. So this is what I mean by a generative model, right? You have some latent space, which might be, for example, a unit Gaussian. And you just pick any random point in there, and then when you do the decoding, it'll actually give you a distribution. So you want to learn a good, valid probability distribution that is fitting for the input data. So to actually impose this sort of regularization, you want to modify the cost term. So not only are you going to be checking out this reconstruction loss, but there will also be a regularization penalty, which is going to be a function of your latent space. So as an example, if you want to impose, this is the distribution I want over my latent space, then this is the probability of any latent space variable having any particular value. And then when you do the negative log likelihood, you'll get this quantity. And this quantity ends up being an L1 regularization term. So when you tack this on over here, it becomes a regularization penalty. So basically, when you want to create a sparse autoencoder, then you have the regular loss, and then you add the term that's down here, and then it'll naturally impose a bias towards this probability distribution for your latent space. And that's desirable because that means you're learning a valid probability distribution. Does anybody have any questions? Yes?
Why do you want to assume the last one?
So this is an example, right? You could impose any sort of distribution you wanted. You could have a Gaussian prior, right? And then when you come down to here, then you'll get some other formula. And that's what you want to use up there. Yes, Jordan?
To add on to Rohan's question, the Gaussian prior promotes sparsity, which is why you want the Gaussian prior for something like a sparse autoencoder.
That's correct,
It's
yes.
very peak at the center, and so most of the values will fall around 0, 0.
Yeah, that's correct. I was going to actually go into an example which uses a non-Laplace. So yeah, I mean, the slide says sparse and autoencoder, but Yeah, L1 regularization in general uses the Laplacian, and that implies sparsity. Yes?
Could you explain again conceptually what is the reason for, like, what is our goal behind imposing this regularization term from, like, by using the distribution?
Right. So this model or this picture, right? You want to have an actual. This is a desirable property. If your latent space actually has a probability distribution associated with it, because then what you're doing is you have this entire continuous domain from which if you sample from, you're basically sampling from a manifold, right? Compared to if you have just random encodings in your latent space and it doesn't follow any sort of pattern, right? Then when you're sampling from it, who knows if it has any reasonable association with any input distribution, right? If you assume your input so if you assume your input comes from a manifold, then you want your latent space characteristics to encode a probability distribution, right? So then that has to be given some formula. So for example, here we're gonna go with the Laplacian because it gives you sparsity.
And the distribution you choose for the latent space just depends on the use case.
Correct. So basically, the way the autoencoder with the sparse autoencoder, if you were to draw a diagram of it, it would still look identical to the undercomplete one. It's just that the loss term is different. So here's an idea. What if you actually make it so the latent space explicitly is encoding a distribution? Not that it's encouraged to because of a loss term, but it's actually, that's what its goal is. So what you could do is have latent space variables explicitly encode a mean and a standard deviation of a probability distribution. And then what happens is when you put in an input, you encode it to these statistics vectors of means and standard deviation. And then given that, you're going to just sample from that distribution, and then you decode for reconstruction. So, and then when you do the loss, you're going to have the reconstruction loss, but also this thing called KL divergence, which I'll talk about real quick. But first, here's a picture of what I mean, right? So originally, instead of having these two vectors, you just have the hidden layer, which is the latent space area, right? But now the encoder actually gets, the results of the encoder actually give you a vector, which is like the mean of this encoding, and a vector, which is the standard deviations of this encoding. So now the encoding is actually a probability distribution itself. And then you get to randomly pick from that and decode. And then if the probability distribution was good, then your reconstruction will still be good, right? So now your network will need to learn to give you good encodings, such that even if you sample from them, and it could be sort of random where you sample from, it'll still give you good reconstruction. And this other thing, KL divergence, that's basically just a measure of how different two distributions are from one another, right? So say you have some distribution in mind, that you want these mean and these standard deviations to actually be reminiscent or like tied to some other distribution, for example, a Gaussian, right? Then when you do the encoding and you do the loss, then you simply check out how different is the encoded distribution from your target distribution. If you look at this equation, it's sort of intuitive, right? So you have P of x and Q of x. So the divergence is given by the value of P of x multiplied by basically the difference between them, right? So if at every point P of x and Q of x are the same, then you'll get log of 1, which is 0, right? And then divergence will be 0, right? So the more different that these distributions are at like all across the entire domain, the higher the divergence will be. So you penalize this. Yes?
Does this mean when you're training, you need like images that have labeled like mean and standard deviation vectors?
No. See, the KL divergence is going to be with respect to an input distribution, and you just know, for example, that the input distribution is going to be a unit Gaussian, right? So a unit Gaussian has a probability function associated with it, P of x, and that's something you could just look up on Wikipedia. Like, what is the PDF of a unit Gaussian? And then you just use that. It's totally invariant to your pictures, right? All you know is that you want your latent space to look like a unit Gaussian, right? So you don't need labeled images of mean standard deviation. That isn't going to be used for KL divergence. Does that answer your question?
Kind of.
Okay. Yes?
So the goal is to explicitly constrain the autoencoder in such a way that the latent space resembles unit Gaussian. Like, let's assume we're using Gaussian, and the KL divergence basis says by the end of this encoding, how different is our latent space distribution? How different is our latent space distribution away from the original Gaussian unit Gaussian that we want to constrain?
Yeah, so there's no like original unit Gaussian, but yeah, everything else you said is correct, right? We want to constrain our autoencoder to learn a distribution in the latent space that resembles a unit Gaussian. And now this is a good way to quantify how different are two different probability distributions. Yes?
So when you're doing the KL divergence, basically, if the two distributions have, in this case, they have the same mean, that's totally not assumed.
In this
The
case?
loss- So this one is kind of assuming that they're very similar, right?
Yeah.
Q of x would like basically anything, right?
Yeah.
And the loss is how different Q of x is from P of x.
Yeah, that's it. Right. And that's really what you want to take away. If you just look up KL divergence code for unit Gaussian, you'll find a nice formula that doesn't involve an integral. But this is like the abstract mathematical, like what the ground truth of what it is. Anyway. Okay, yeah, we gotta go fast. So anyway, like we can actually kind of sidestep this whole probability distribution idea if we give our autoencoder a bigger challenge. So now what we're gonna do is play a game with our autoencoder where we actually corrupt the input, and we still expect the autoencoder to recover the uncorrupted input. So it's no longer gonna reconstruct exactly what it was fed, but it's gonna take out the noise that we put in. So now not only does the autoencoder need to learn a representation, but it needs to be able to understand what is noise and what is not. So you apply any arbitrary corruption function, and you want it to, and you expect it to, and you give it this new modified loss function. So it needs to learn the probability distribution of the input because otherwise it won't be able to take out the noise. So this is what you want it to do. You want to be able to give it some input, which is corrupted. This is the original. You want to corrupt it, and you want it to be able to recover what it was before it was corrupted. And they can actually learn this pretty well because what they end up doing is learning this. Because the corruption function can actually corrupt it in any arbitrary fashion, and you still want to be able to reconstruct things that are all along this line, then with every decoding, you'll learn one of these green arrows, right? And that green arrow will help point to where is the actual manifold. And so from that, you can implicitly learn a manifold. So a similar idea is to basically look at the actual derivatives of the latent space characteristics. So you want points that are close to each other in input space to also be close to each other in latent space. That sounds intuitively reasonable. And so if f of x, the encoder, is a continuous function and has small derivatives, then this property will basically hold. So the way you do this is you check out this quantity, Frobenius norm of the Jacobian matrix. So I'll go over what both of those things are. And again, this is just like another regularization strategy. So you add this to the reconstruction loss. So Jacobian matrix is basically just a matrix of all the different derivatives of all the different input directions. And a Frobenius norm is just like it's just an extension of the L2 norm, but basically to matrices. So now what you'd be doing is you want to be taking the Frobenius norm of the Jacobian matrix, right? So what that would be doing is constraining the size of the derivatives of the encoding function with respect to each of the different input directions. So if you're doing that, then you'll be able to keep neighborhoods in input space. You will make those into neighborhoods in latent space, and that's desirable as well. So they're called contractive because they contract neighborhoods into smaller neighborhoods generally. And so another property that you'll see is that the Jacobian matrix, most of its eigenvalues will go below 1. And these are directions that have been contracted. But some of them will actually remain above 1. And these are the directions that actually explain most of the variance in the data. So this is an example of learning a manifold, which I don't think was done with an autoencoder, but is just done for visualization purposes. That you can imagine that when you're learning this data set of MNIST, which is handwritten digits, that data is in 784 dimensions because it's 28 by 28. But at the very end, you could project it down to just 2 hidden units. And you could put those 2 hidden units as 2 coordinates, first dimension and second dimension, and you could put them on an XY plane. And what do you notice, right? Things that are similar in input space, aka the same digit, ought to be near each other in latent space, right? So this is more or less the intuition behind contractive autoencoders, that you want the derivatives that if you change x ever so slightly, f of x shouldn't change a whole lot, right? F of x should also remain rather small. So that is this idea of continuity and keeping small derivatives. It's usually these dots, for example, these purple dots in this green neighborhood that end up giving you your errors in the end, right? Because what the network will learn is to associate that entire region of space, that entire region of latent space, to be of one number. But then if you're unable to actually keep everything grouped together, then that's where you usually will get your errors. So all in all, like, this is the key. I think you asked about why are we doing regularization. And basically it comes down to these 2 principles that you want to be sensitive to inputs because otherwise you won't be able to do reconstruction very well. You have to be able to know down to the pixel that this is what the input is like and this is how I can get that very pixel back, right? So that will give you good reconstructions of data. But at the same time, you need to be insensitive to inputs because that'll lead to overfitting, right? So this is why you have to balance your autoencoder, you have to constrain your autoencoder with regularization penalties. Because this way you'll learn the entire data distribution, not just the very fine points that you picked out of your data distribution, right? If you want it to generalize to a test set, then it has to learn the underlying manifold of data. And that's why we do regularization. So as a matter of fact, when you compare denoising and contractive autoencoders, they're actually sort of trying to do the same thing. Because denoising autoencoders make the reconstruction resist tiny but finite size changes in the input, which are the noise. And likewise, contractive autoencoders are trying to make the feature encoding function resist infinitesimal perturbations in input. So more or less, in the end, the result is that contractive autoencoders, or denoising autoencoders, when taken to the limit, are essentially equivalent to contractive autoencoders. It's just a matter of implementation preference for you now, right? You can either choose to add noise to all of your inputs a little bit, or you can choose to do some sort of regularization thing where you do derivatives. But in the end, they're still working on the same principle, which is that entire principle of being insensitive to your inputs, right? So you can imagine that if I just made that like that noisy image, it would be very close to the unnoisy image in input space, right? And I want the decoding function to be insensitive to that, right? I want the latent representation of the noisy image to still be very close to the latent representation of the unnoisy image. Does anybody have any questions? Yes?
Is one like preferred due to like speed or accuracy in terms of implementation?
Yeah, that's a good question. I think I have it here that calculating the Jacobian matrix can be expensive, but you can still work around that because the Jacobian matrix should be of the entire encoding function, right, of f of x. But you could break that down into a bunch of different Jacobian matrices for each layer, right? So depending on the architecture, you might find it that doing the Jacobians for each layer will still be cheap. And I think in the limit that should be good because when you're doing the noisy one, then that involves more hyperparameters because you need to pick how much noise are you going to add, right? If you add too much noise, then it'll be too hard, right? And if you add too little noise, it may not do what you want, right? So contractive is sort of like a more theoretically justifiable thing. That's what I was saying, that denoising in the limit becomes contractive. Do you have a question? No? Yes?
So for contractive autoencoding, the idea is that when you have 2 separate inputs that are different
Yeah.
by by a certain amount. We want their distance. We want the difference in the space to also resemble the same difference in the original space. And so we try to minimize the difference between the two, right?
Yeah, so you want them to resemble the difference, but still you want it to be small, right? It's still going to contract neighborhoods. But you shouldn't have it that if they're very close in input space, they suddenly become far apart in latent space. That would be unreasonable. But yeah, I think you got it. So generally what you can do is, for autoencoders, outside of just learning representations, or I guess the dimensionality reduction is a big part of it, that you can use autoencoders as basically your go-to unsupervised deep learning strategy. And something else that you can do with them, which I found interesting, was information retrieval. That if you have a key and you autoencode it, that could be the value of your key. And so you can use autoencoders for information retrieval. That's pretty cool too. But anyway, we have to move on to representation learning. So representations are very important. So I found this picture on the internet. I found it funny, right? Try doing long division with Roman numerals. And I don't even know how this is working. But basically, if you don't have good representations in STEM, then you're kind of screwed. And so a lot of the big changes in history actually just came from learning good representations of things. I've got some examples down here, right? So, and most of this entire field of machine learning and deep learning is actually based off of having good representations, I would say. So the point of representations is making subsequent tasks easier. So for example, when you have a feed-forward net, that's what the hidden layers are actually doing. They're learning representations so that the output layer can just do a nice softmax or sigmoid on that representation. And convnets are designed the way they are because the filters are learning representations, or they're building up representations through their filtering. And autoencoders, their entire deal is building representations. And so we're going to be talking about what makes representations good or bad. So we'll start with symbolic representations. So you can imagine you have a vector with n spots in it, and each spot ends up like symbolizing one category or one class. So the simplest one of these would be like a bag of words model, such that every spot, when there's a 1, you're encoding that word, right? And this is a very simple model or simple representation scheme to build, but the problem is that there's no notion of distance between two different encodings, because 1, 0, 0, 0 is just as far from 0, 1, 0, 0, 0 as it is from zeros and then 1 at the very end. All of these are sort of discretely mapped, and there's no notion of distance or similarity. And as a consequence, there's no way to actually capture features in these representations. And a lot of the, for example, categorical variables that you would be putting into something like a logistic regression, the go-to way to do it is just to use one-hot encoding. But that suffers from these problems, because ultimately, for a vector of length n, you basically only have O of n possible representations. So a better way to do it would be to have a distributed representation, where every single different vector that you could build is a different category. So you want to build, for example, word embeddings, such that you can map a word to a vector, and all of this vector space is parameterized to be all of the possible words, basically. And now in this idea, you can encode similarity and distance measures between different representations. And whereas before, if a word was if you have two words, for example, 1, 0, 0 is dog, and 0, 1, blah, blah, blah is cat, now you could have each spot actually represent different features. For example, how many legs? Yeah, so number of legs versus is a dog. And so much of the art of deep learning in modern data science is actually building good features, feature engineering, right? And if you want to build good features, it'll be useful because this will have a lower dimensionality for the same number of possible representations, an exponential number of representations. And if you're able to actually build distributed representations, then you can do very cool things like this. For example, on the very left is a representation of man with glasses. So basically man plus glasses. And in the middle is a representation of man. So if you're just going to take the vector of man plus glasses, subtract man, and add woman, then you can get woman plus glasses. And that's what this deep learning model was able to do. And so that's much of the art of deep learning at this point, is learning good representations for these sorts of generative tasks. So distributed representation is more or less implies that you've learned a data manifold, which is useful. And you also have these benefits. So 2 weeks ago, I talked about greedy layer-wise supervised pre-training. And today we're going to talk about greedy layer-wise unsupervised pre-training. So if you remember from last time, the way that worked was you build it layer by layer, and every time you add a new layer, you freeze the layers before it. And you basically train the next layer for the labels. And that way, that layer will have to leverage the representations from the earlier layers to try and do classification or regression. In this case, what you can do is freeze the earlier layers and have the very last layer be the hidden layer of an autoencoder. And you try and have it encode the image or the input. And so through this, you still have the same principle of leveraging representations. And that is this technique. And this was actually used a lot earlier. And it's not as useful anymore, but it's still a cool technique to try and understand. And so it works for two reasons. One is that before you, and this is done on tasks that are going to be supervised learning tasks. It's basically picking out the parameters before you even do any sort of supervised learning. And so you're working on the assumption that if you pick good initial parameters, it'll have this regularizing effect, that it'll work for any sort of inputs. And this isn't super well understood, but at the same time, what you're also doing is learning the input distribution, and that'll help in mapping your inputs to your outputs. And so by doing this, you can basically learn good word embeddings, and it may also be very useful for when you're doing semi-supervised learning. And what it looks like is basically like this, that if you were to start with initial parameters randomly and start doing your supervised learning regime, then there's a lot of variance in where the parameters will end up going. But if you do the pre-training, then because the parameters set has already learned a bunch of representations for the unsupervised learning tasks that it was given, then it's a lot more streamlined in its training for the supervised task. Does anybody have any questions about this? Yes?
What do the horizontal and vertical axes represent in this plot? They're not labeled.
I think those are just like parameter coordinates, but the colors represent time. So this is from the deep learning textbook, and it was actually saying that the redder it is later in time. So for whatever reason, when on this example, when they did unsupervised pre-training, then like they actually went in opposite directions. And I guess that's like the better end. Like it could be that there's like some sort of ridge here, and this is a local minimum and this is a better minimum. I don't know. But yeah, just imagine it as moving through parameter space over time. So representation learning is also very useful for if you want to work on multiple tasks. So 2 weeks ago I talked about transfer learning, but we will be discussing this in greater depth today. So the key idea is that if you have one distribution that it's easy to learn, but it shares some certain characteristics with the second one, then you can leverage the representations that you learned from the first one and use those to help you learn on the second one. So transfer learning has like actually sort of a precise definition where your input distributions are similar, but the labels are very different. So an example would be that the first distribution, they're both pictures, but is of dogs and cats, and the second one has horses and cows. So the low-level features of the inputs are very similar, right? Because you're going to be taking pictures, and pictures have many characteristics that are common. But the labels are very different because you're going to be picturing very different kinds of animals. But yet, learning on D1 will still give you a foundation for a latent space. and then you simply adjust the network to learn on D2. And basically, the flip side of it is domain adaptation, where the labels are actually similar, but the inputs are sort of different. So an example would be speech to text. So in this case, you need to take audio recordings and still spit out English. And you have to have like syntactically, semantically good English. And so in that case, the labels are similar because you still need to be able to map audio to English. Yet the speakers may have very different voice characteristics and speaking patterns. And so as long as you have sort of a representation of what is spoken English sound like in the abstract, then you can sort of fine-tune that for the different input distributions. And so this is called domain adaptation. And so I guess the general idea of multitask learning can be summarized in this picture, where you have the original thing, x and y, and then you're going to move it up to h of x, h of y. And you need to basically learn different parts of this diagram depending on whether you're doing transfer learning or domain adaptation. And more extreme examples, you can actually do this with literally using one example from the second distribution. Because if the hypothesis is that learning on D1 actually is able to separate the data into two discrete clusters, and then you only need one example to figure out which cluster is that label from D2 from, then you can infer that everything in that cluster is one label and everything in the other cluster is another label. Yes?
So this implies that like one of the cluster D2 is part of one of the clusters, and not D2, I guess, in this case, would be part of the other cluster, right?
Not quite. I think what it means is that D1, when you learn it well enough, you learn the representations well enough, you can cleanly separate it, like almost like linearly separable kind of, into two clusters of category D1 sub 1 and D1 sub 2, right?
Yeah.
The two categories in D1. And then if you apply that same sort of transformation onto D2, then you're inferring that that will also cleanly separate D2 into two clusters,
Okay.
right? So it's just that the classes might just be super different in both D1 and D2 from one another, that they're very cleanly separable.
Okay.
And now if D1 is very easy to train on, then you want to use that to your advantage, right? And then that's what you do. And then you can actually do this with zero shot, where you don't even use a single training example or a single labeled example. And so what you do is you basically learn some context about the distribution. So T is sort of like D1, and X would be D2. And an example would be this, that T is a bunch of sentences. Like cats have 4 legs, they have pointy ears, they have fur. And then X is images, and then you want to be able to still infer whether or not the image is of a cat. So you're learning this other distribution of probability of Y given X and T. So representations, what you usually want is you want to know whether or not the label, you want to have it such that the label actually influences your representation. The fact that the label is a cat should influence your representation to reflect that, right? And so if they're correlated in like a very clean, disentangled way, then you can clearly map changes in the label to changes in your latent space. That would be a good thing, and that's something you want for disentangled causes. At the same time, you want representations that have sparse feature vectors, because that way the different features are going to be independent from one another. And so oftentimes, when you disentangle causes, you'll be able to separate out the different features into different parts, or into, yeah. And now ideally, this is what your distribution should look like. And the probability of, and the marginal probability of X will end up just being an expectation over your different latent space variables. So you can view this as the ideal latent space variables actually being causal to X. And likewise, since you're ultimately trying to figure out the probability of some label given X, and from Bayes' rule you know that that depends on probability of the priors on X, knowing that H being causal is good. So, I mean, I guess this is sort of just like a deep dive into like what is it that we're fundamentally trying to learn about H? We're trying to learn an H that has a causal relationship with X and Y. But the problem is that there are way too many causes for why things look the way they do in real life. And like even for us when we're doing perception-based tasks, it's really hard for us to really pay attention to everything at once. And so you have to figure out what is it that's really important and when you weight different causes. And so this is an idea called saliency. So an example would be autoencoders fail to find they fail to reconstruct small objects, which are still salient, like ping pong balls, like this. So I think this is a robotic arm with a ping pong ball and just very low res images. When you reconstruct it, because the ping pong ball is so small, it fails to reconstruct it, even though it's very salient, right? The problem is that we've been using mean squared error, and mean squared error works under the assumption that salient things exist in a large number of pixels, and you want to be able to capture all of those. So under mean squared error, you can sort of forgive that you didn't pick up that ping pong ball because it's a difference in a small number of pixels. So something that we'll be talking about more in this class is the adversarial approach, where you basically try to learn what saliency really means more than just numbers of pixels by having another network which is trained to actually figure out whether or not the reconstruction came from an autoencoder or came from the input distribution, right? So now you've abstracted away the task of learning saliency into a game between two different networks. And that actually works a lot better. So for example, if you wanted to reconstruct a human face, an ear actually has a very small number of pixels in which there's a difference between the surrounding area. And so in the reconstruction, oftentimes, if you just use mean squared error, the autoencoder won't bother to actually learn the boundary of an ear. But if you have another network which is trained specifically to try and figure out whether or not the image came from an autoencoder or from the input data, then it'll clearly pick up soon that if there's no ear in the picture, then clearly it came from an autoencoder. So to adapt, the autoencoder will learn to make ears. Yeah. So in conclusion, we talked a lot about autoencoders and representation learning, but I guess what I want you to understand is that autoencoders and representation learning are very intimately tied. At the same time, representation learning is all over the place with deep learning in general. I talked about it in the earlier slides, like feed-forward nets, conv nets, they all use representation learning too. And it really got me thinking, and ultimately I guess what I wanted to leave you with the thought is that maybe all it is about intelligence is just representation learning. And so in the future, I think much of the advances in deep learning will come from how we choose to do representation learning. That's it. Any questions? All right. Thanks, guys. Should I start? What's that? Okay. No.
very like low stretch, no.
Is there a way to do notes, like to show the notes? Like,
I don't know. Yeah, I've never done it.
okay, yeah, whatever.
It's okay.
Because I had some notes on the slides.
Cool. Are you good to go?
I guess.
Do you have access to the questions?
There's somewhere here.
Okay. As long as you have access to them.
Yeah, I can do that later, though, right?
Okay. Yeah.
Okay. Also, this might be kind of short. I don't have
That's
notes.
okay.
Okay.
The length isn't an issue. I'll just make sure to like discuss like the main points of the paper and what they did.
Yeah.
And I guess we can try and answer the questions if you can.
Okay.
Yeah, and maybe if you can, like facilitate the discussion.
Okay.
Yeah. Don't worry if you end early. Like that's totally fine.
Okay. Cool.
We can start in like 1 minute.
Yeah.
Actually, we start now.
Okay. All right. I'm Austin, and the paper I'm presenting is on visual semantics alignment. So basically, what we have is like a bunch of data sets with pictures and like a 5-sentence description or so on what's in the picture. So we'll have like a picture like this, and it'll be like there's a tablet of the newspaper next to like a plate of fruit and yogurt with like flowers on the table or whatever. And then from that, we will create a model that can train it so that we are able to identify images and also give them kind of a brief description as well, based on the description of the entire image. Yeah. So the steps, the two main steps are like alignment and generation. And so alignment uses a CNN to kind of identify 19 images, and then it uses a bidirectional RNN to basically link those to a bidirectional RNN to link the words to the images in a way, along with multimodal embedding. And then the second step is generation, which basically will take the inputs from the alignment and kind of generate our final model. Yeah.
Multimodal embedding, is that like we have one embedding for like the image and a sentence?
Yeah, so
I have an embedding that describes the image and its caption. Is that what it is?
so basically we will have it'll kind of link the images with the words.
What
Yeah.
is a multimodal embedding, I guess, is the question.
I'm not like
In the class note, I would explain
totally sure.
multimodal embedding. This is all we were
They're embedded in the same latent space so that you can take similarities between them by using that power.
Yeah. Cool. Okay. So for alignment, there's kind of several steps. The first step is using your so first we want to identify our like 19 images, right? So they train on ImageNet, which is just kind of like a data set of a bunch of images, and then they use that to identify the top 20 images in all our secondary image sets, which will have our images and our descriptions. And so we have our 19 top images and also the full image as well. So we have a vector of 20 images. And then all these 20 vectors are in like h-dimensional space. And so we want to also have words in h-dimensional space that can map to those vectors. And so we use bidirectional RNNs to basically create h-dimensional features to map with those words. And then we use the dot product which basically finds like our best image and sentence alignment and kind of matches like our best image with, or sorry, our best words with our images that we have. Okay, and then the generational model uses, its input is the output from alignment. So we'll have our like 19 or 20 images or so, and also like the top words that align with them, and it'll basically use that and use a multimodal recurrent neural network to basically kind of predict like a sentence or kind of like a phrase to go along with our image. And then that will kind of give us our final output. And then performance-wise, their model performed pretty well compared to other previous work. They have their R at 1, R at 5, R at 10, and like medium R ratings, and it all performed much better than all the previous work. And this was for their Flickr 30K data set. They also ran it on Flickr, I think, 130K, or they ran it on another Flickr data set as well, and MS Coco. Yeah. And then there are some limitations though. With the second part, with the generation model, it doesn't always work at, like, it can only work with like fixed image resolutions, so it is kind of limited there. In terms of applications, I guess you can use it for like describing features in pictures, and that's pretty much it. So questions, or should I open it up for discussion, or? Okay. Yeah.
Okay, so my question was, so during training, you basically have an image and then you have a string that basically says something describing the image, and you're basically trying to separate different components of the string, separate different components of your image, and then match together which regions of your image should match to like certain string descriptions. But then when you're performing inference, you don't have access to a string description of a new image. You just have the image. So is it just generating captions from that alone?
Could you say the question again?
So from my understanding on how this is implemented,
Yeah.
when they're performing training on this algorithm, that first stage where you have to find some multimodal embedding, basically you have some text that describes this image. That it's not in any given order, it's just some description. And then you have an image, and then you feed that image into a convolutional neural network, and you basically get out 20 sub-images, and then you have your description, you feed that through bidirectional RNN, and then you get, let's say, maybe 20 more, or however many more vectors that represent different components, not necessarily words, but like different components of that description. So when you're performing inference, you don't have access to descriptions of an image, so it's just generating this. Is that correct? That's my understanding.
Yeah, I think that's correct. Yeah.
In the paper, it says that the RNN is trained to combine a word in the previous context to predict the next one. So what it does is, what I presume it does is, given like the first bit of it, it tries to confirm the represented images it gets, generate that kind of sequentially going through the image. It does generate it from the image. My question was actually, for the procedure generation, how does it, I guess, learn the ordering of the image vector? Is it just arbitrary how it structures a sentence, or is it kind of, so like how is it, well I guess this is more one question, how is the loss generated for the sentence?
How is the I'm not entirely sure. Sorry. Any more questions, or should we open it up for discussion? Okay.
Okay, so in groups of like up to 5, you should discuss your questions for the paper. If you look on Piazza, there's a, well, on the post that says reading group assignments, there'll be a list of questions for today's paper. You should get in the group now, or else we'll contact all of you really awkwardly. I like it.
Yeah, just reading questions.
Okay.
Here it's stories on that. But I don't know if that's it's like that. It actually does come then like it's a lot less. It's a lot less. Because if you read it like supposed to be down, wow, just
Like, okay, so at a time, I would think, well,
these kind of if you get something that are able to parse together the variables and more really
We already have an idea.
yeah, I was gonna start you're not like you don't want to you're not trying to translate from one medium to the other. You're trying to translate code through or in a large sense, ideally, intent to a
Yeah.
because there's a terminology oh, correct. Yes, I have. I need to read them. I read them until I go back and like, oh, yes, I did.
But I read about it, I just understand
Whatever this was. Just like the people.
Yeah.
Yeah.
It does
Yeah, it's good.
Yeah.
And so it's a lot of people
Just answer the ones you want, and it's really up to you. That basically they're just a lot. Hi guys, we're gonna answer the questions now.
Okay. So how is the test data structured? This was kind of answered in the presentation. We have like all our images with like 5-sentence description of like what the images are. How is the accuracy of a description determined? They had their R at 1, R at 5, and R at 10 model to kind of calculate how accurate the descriptions and identification were. is it possible to use a single model trained end-to-end instead of two separate models? Currently, at least for kind of what they had set up, they weren't able to kind of reduce it into one model. They had to kind of split it up into two. I'm not sure if maybe like doing a different approach might be able to reduce it to just one model, but with the approach that they had, it kind of had to be separate. Does the model organically predict the relations between two objects? I don't know what you mean by organically, but it definitely like uses the placement of the words to kind of with the RNN, it kind of uses the placement and ordering of the words to kind of determine like what the description would be. How well does this model identify relationships and interactions between objects when there are multiple subjects in an image? Well, in all our cases, there were like 19 like images that were being identified, so I assume that it would identify those relationships pretty well. Are there any questions that anyone specifically wants to hear up here, or no? I guess that's it then. Okay, thank you.
Okay, I'm gonna wrap up. Thanks, guys. Next time we'll talk about what's your lecture on? Ooh, yeah, and like a lot of Monte Carlo stuff. Sweet, yeah. Next week's will be cool. So proposals due tonight. Make sure you submit it. Otherwise, you won't get credit for the proposal. You can still do the project, but 2 weeks from today, your first interim is due. So you have, if you go look at the project description on GitHub, there's a timeline for, the syllabus. If you look at the syllabus, there's a timeline for when you just submit each of your interim submissions. So today's week 6, the 6th class, and so the proposal's due today. Do you mind opening the GitHub just so I can show them? Cool. Deep Learning. Cool. And then syllabus, sweet. And then I think it's on there. Yeah, okay. So proposals due today. In 2 weeks, your milestone 1 is due. So you need to give us like a progress report, something that shows us that you started working on this. Here's what I've thought of. Here's what I've tried. Here's what I'm going to try. Some kind of like 1 page filled with maybe a figure, maybe some papers or some code or something that you've scrapped together. Doesn't need to be super official. So that's in 2 weeks from, just to show us that you've started. You started to think about this. You're not going to do this all last minute. 2 weeks after that, week 10, you have like a bigger submission due. It's like a kind of like a bigger interim where you have to give us some preliminary results. So that's kind of 2 pages, and that's kind of to get you started on your actual final project write-up. So the idea is that for milestone 2, most of the writing that you do for that can be transferred for the final project itself. So the milestone 2 should be kind of like a project type format, like an intro, data, previous work, etc. And then the final submission, the final project, will do the last day of class. Yeah. Any questions about that? So the reason we did this is I know it like sucks to have so many submissions, but it's the only thing you have to do for the class. And by forcing you to do it, it'll keep you on track, and we'll make sure that you guys actually do something. If you don't, you get a no pass, and that's your prerogative. But I don't want to no pass you. So, and I want to see some really cool projects. I was looking at proposals, and I saw some really cool proposals. So I really hope you guys are able to pull some of these ideas off. And you're more than welcome to run your idea by us, or come talk to us about what you've tried and see, and maybe ask us some questions about why some things don't work and other things do. And so we'll be around if you guys want to talk. But I think we're done for today. Thank you.